This is the presentation on impulse and momentum. What is momentum? Well, in all the physics concepts, the only one I'll allow a student to define using its equation is actually momentum, because it's very simply just an object's mass times the object's velocity. Some people talk about momentum as being inertia in motion, V-L-O-C-I-T. Okay. Mass is inertia. Remember, mass is a measure of an object's inertia. And momentum is not only how much inertia the object has, how much force it takes to accelerate it, but it's also the velocity, how fast it's going. The equation is very simply P equals mv. Momentum is P. That comes from the term persistence of motion, which is what it was called before it was called momentum. The units of momentum, well, it's a mass times a velocity. And so the units are kilograms, meters per second. So a very simple calculation: if momentum is mass times velocity, an object has 25 kilograms of mass and it's moving 12 meters per second. So 25 kilograms times 12 meters per second would be 300 kilograms meters per second. Okay. You need to be able to solve for any of those three variables given the other two. So if an object has a mass of 50 kilograms and momentum of 125, well, if momentum is mass times velocity, then velocity would be momentum divided by mass. So that'd be 125 divided by 50, which is 2.5 meters per second. So if you're going to change the momentum of an object, think about what momentum is. It's mass times velocity. Well, you're generally not going to change the mass. What you're going to be changing is the velocity. And to change the velocity means that you're going to accelerate the object. And if you're going to accelerate it, that means you have to apply a force. So an application of an external force will change the momentum of an object. So impulse is the second quantity that we need to talk about. An impulse is a change in momentum. And in order to change momentum, you have to apply a force. And so the equation for impulse, and by the way, the symbol for impulse is a J. The equation for impulse equals the force that you apply to change the momentum times the time for which you apply it. Now, I say here that there are two equations because the definition of impulse is that it is a change in momentum. And so it has to be delta P, which is the final momentum minus the initial momentum. So you can calculate impulse by using force times time, and you can also calculate impulse by finding out how much the momentum has changed. The units of impulse are Newton seconds. Force times time, newtons times seconds. Now, if impulse is a change in momentum, then the units have to be the same as momentum units, and a Newton second is equal to a kilogram meter per second. Remember, a Newton is a kilogram meter per second squared. And if I multiply that by seconds, that second cancels with one of those. And you can see it's a kilogram meters per second. But we use this unit for impulse, and we use this unit for momentum. I know that sounds silly, but that's just how we do it. If a force of 100 newtons is exerted on an object for 0.25 seconds, what's the impulse? Impulse is force times time. And so 100 newtons times 0.25 seconds is 25 Newton seconds. If an object undergoes an impulse of 150 Newton seconds during a time interval of 0.5 seconds, what's the average force? Impulse is force times time. So that average force is equal to impulse divided by time. So 150 divided by 0.5, and that's equal to 300 newtons. Okay, so impulse is equal to a change in momentum. Well, a change in momentum would look like the mass times the final velocity, this is the final momentum, minus the mass times the initial velocity. You can factor that mass out, and it ends up being m delta v, or mass times a change in velocity. And impulse is also force times change in time. So if impulse is this and impulse is this, then we can write those two things as being equivalent to each other, and this is called the impulse momentum theorem. It's also a statement of Newton's second law. I think that's what the next slide shows. So yes. So this is just a statement of Newton's second law. And you can see that if you try to get the force by itself, by dividing both sides by time, that would leave a force on that side and a mass times change in velocity over time on this side, and this is just ma. So this is the impulse momentum theorem, and it is simply a variation, another way to state Newton's second law. A 2,200 kilogram vehicle, it can be traveling at, or vehicle, I don't know, that should be I guess, traveling at 26 meters per second. That would be our initial velocity. Can be stopped. Stopped means the final velocity is 0, or v2 is 0, in 21 seconds, and there's our time. Find the average force. So force times time equals mass times change in velocity. Force equals mass times, now remember, a change in velocity is v2 minus v1 over time. So that's 2,200 times 0 minus 26 all over 21. I think when I originally made this, I meant to make that a 22 seconds. Let me pull up my calculator. It takes me just a second because it's my phone. So 2,200 times 26, divide that by 21, and I get a negative, because this is actually a negative 26 right here, 2,724 newtons. I'm solving for force, it's newtons. Okay, so given any three of these quantities, you need to be able to solve for the fourth. So conservation of momentum works very much like conservation of energy did. And just like in conservation of energy, it means that the momentum remains constant as some physical change happens. And for momentum, generally we're talking about collisions or explosions. The explosions are not exciting things. It's just when one thing becomes more than one thing. So for a collision occurring between object 1 and object 2 in an isolated system, we'll define that in a minute, the total momentum before the collision is equal to the total momentum of the objects after the collision. That is, the momentum lost by one object is equal to the momentum gained by the other. And generally, it's a statement something like this. Although there's no equation of conservation of momentum, you kind of have to write your own equation for each problem. You may only have one object here. If a gun shoots a bullet, then you have a gun and a bullet making a single object here with a single velocity, and then it's a gun and the bullet separately after. You may have two objects before and one, like two cars hit each other and they stick together and move off as a single object. So your equation might look a little bit different depending on the situation. But the important thing is that your initial momentum is equal to your final momentum. A closed system is one that has no gain or loss of mass. And an isolated system is one with no external force acting on it. Okay, internal and external forces. Internal forces are forces that act within a system. So if you're sitting in your car and you push on the steering wheel, you're not going to make your car move forward because it's pushing back on you, and those are internal forces. But if you open the car door and you put your foot on the outside and you put your car in neutral and your car's not really heavy, you can make your car move forward because the frictional force exerted on your foot by the road when you push against the road would be an external force, and that can accelerate your car. Okay, when a firecracker explodes, say we have a firecracker that looks like this. When it explodes, it breaks into pieces, and those pieces are all moving off in different directions. Conservation of momentum says if the initial momentum is 0, like that firecracker that's just sitting there being still, then the final momentum also has to be 0. So if I added the momenta of each of these objects together, I would get 0. Momentum is a vector quantity, direction matters. And so each of these little pieces would have x and y components to their velocities, and the sum of the x components would be 0, and the sum of the y components would be 0 in order to make momentum conserved in every dimension. The recoiling cannon. The word recoil, if you shoot a gun, the bullet goes in one direction, the gun actually moves in the other. It's conservation of momentum. And that gun motion, that backward motion is called recoil. So a recoiling cannon, if I have a cannon of mass 750 kilogram and it shoots a cannonball of mass 30 kilograms, and the cannonball has a velocity of 20 meters per second, how fast will the cannon be moving backward? So beforehand, I have a cannon and it has a cannonball in it. And so I have the mass of the cannon plus the velocity of the cannon plus the mass of the ball plus the velocity of the ball. Well, they're both 0. So I get a big fat 0 on this side because it's not moving. And then the ball is moving with 20 meters per second of velocity. And so the cannon is going to be moving in the other direction with some unknown velocity v. And so on this side of the equation, we have the mass of the cannon, 750 kilograms, times its velocity, which we don't know, plus the mass of the ball, 30 kilograms, times the velocity of the ball. So we have a 600 here, 750 v. And so if I solve for that, I'm going to get a negative. These are both positive over here. I'm going to move one of these terms to the other and divide by 750, and I will get negative 0.8 meters per second. It's negative because it's moving to the left. If we call positive to the right and negative to the left, then the cannon itself would have a negative velocity. Remember, velocity is a vector, and momentum is also a vector. Energy is not. We've talked about collisions before, elastic and inelastic. In an inelastic collision, and that's typically things bouncing off of each other, a perfectly elastic collision, the objects would bounce, and kinetic energy is conserved. In an inelastic collision, sometimes it's objects, a perfectly inelastic collision would be when the objects actually stick together, but they don't have to stick together for it to be inelastic. All you have to have is some energy lost to something, making noise, changing shape, denting. So kinetic energy is not conserved in an inelastic collision, but momentum is conserved in both types of collisions. Example, a bullet of mass 0.01 kilograms is shot at a speed of 30 meters per second at a block that is stationary. And the block has a mass of 5 kilograms and the bullet's 0.01. I find it helpful to draw pictures like this. And then after the collision, the bullet has lodged itself in the block, and the block and the bullet fly off with some unknown velocity. Find the speed with which they fly off. So I'm going to have the mass of the bullet times the velocity of the bullet plus the mass of the block times the velocity of the block, and on this side that's 0, equals the total mass of everything times its velocity. So I have the bullet mass, 0.01, times its velocity, which is 30, plus 0, equals the total mass, which is 5.01 kilograms, times this unknown v. And so on the left-hand side, 0.01 is going to be 0.3, 0.3 equals 5.01 v. And pull up my calculator again. Hold on just a second. Okay, so 0.01 times 30 equals 0.3 divided by 5.01, and I get a velocity of 0.06. I rounded that a little bit. Velocity is 0.06 meters per second. Okay, so we've had examples where one thing becomes a couple of things, the cannon and the cannonball, and now we have an example of where a couple of things become one thing. A 45 kilogram student, this is another one thing becomes multiple things. The student is riding a skateboard, and then the student jumps off, jumps off backwards with a velocity of -1 meter per second. The student has a mass of 45 kilograms. And the skateboard goes on its merry way. And the skateboard has a mass of 7 kilograms. And we don't know how fast it's moving. Beforehand, the student and the skateboard, which have a total mass of 52 kilograms, is moving to the right at 4 meters per second. So my equation is going to look like mv, I'll do a big M because it's the total mass, equals the mass of the student, I'm going to call it a boy because skateboard and student are both S's, times the velocity of the boy plus the mass of the skateboard times the velocity of the skateboard. So 52 times 4 equals 45 times -1 plus 7 times the velocity of the skateboard. So 52 times 4 is 208, -45 plus 7 VS. So 208, that's going to be plus 45, because that's going to be positive when you move it to the other side. So that's 253 equals 7 VS. So divide by 7, and I get the skateboard moving at 36 meters per second. That's actually really fast. Okay. No, but I'd already had the answer there. So, and our last example, you're going to see something like this on the quizzes and the tests. So I thought it's a pretty simple thing, but I don't want you to get confused. Given the following information, determine if the collision is elastic or inelastic, and if momentum is conserved. So what we're trying to figure out is initial kinetic energy equal to final kinetic energy? Not of an individual thing, but of all of them added together. And is initial momentum equal to final momentum? And so it's really easy. Here are my initial momenta. And so 0.5 plus -2.25, that equals -1.75 kilogram meters per second. And the final momentum is -1.38 plus -0.37, and that's -1.75. They are the same, and so momentum is conserved. And now we'll look at our initial and final kinetic energies. Pay attention to the headings of the columns because I might not have them in the same order that you'll see them later. So 1.69 plus 0.25 equals 1.94. Notice all the kinetic energies are positive. Kinetic energy is a scalar quantity. It is always positive. 1.89 plus 0.05 equals 1.94. So kinetic energy is conserved, and so it is an elastic collision. So momentum is conserved, and the collision is an elastic, not an inelastic, but an elastic collision. Okay, good luck on the quizzes and the tests, and I hope you found this helpful.